Welcome to the module 3 of engineering geology titled Influence of Geological Structures on the Civil Engineering Constructions. I am Professor Mohammad Masroor from Department of Civil Engineering, AMU Aligarh. As a student of geology, you know that all rocks are deformed, and this deformation is the result of rocks undergoing different kinds of forces and stresses in their geological past. These deformation structures, they create different kinds of discontinuity surfaces in the rock mass, and they also result in dislocation and repetition of rocks. Civil engineering structures, they are made either on soil or on rock, and whenever they are made, they are founded on the rock mass, then these structures, they play very important role because they are going to control the overall behavior of rock mass in case of loading by civil engineering structures, or also in case of unloading when we go for large scale excavations, for example, for construction of tunnels, for construction of underground structures, and for construction of dam foundation. As you know that we have different kinds of structures, primary structures and secondary structures. In primary structures, we will include the different kinds of contacts between the rocks, different kinds of layers, for example, lamination and bedding plane in sedimentary rocks, foliation plane in metamorphic rocks, as well as flowage planes in volcanic rocks. Apart from this, we have deformation structures, for example, joints, for example, shear zones, folds and faults. All these structures, they vary in different sizes, starting from few centimeters to tens of meters, and even some faults thousands of meters in length. Now, when we start working in the rock mass, the most common discontinuity surface which we are going to encounter is either contacts or laminations or bedding planes or foliation planes and the joints. Joints are ubiquitous as far as their presence in rock mass is concerned. Without joints, we do not have any rock present in the natural conditions. There may be chances that you may not have shear zones, you may not have fold, you may not have fault at a particular site, but it is very difficult to find any rock mass without joints. So, joints are going to play the most important roles apart from the contacts. As you know that once you have contact between two rocks, that means across the contact you have two different rocks, and once you have two different rocks, they will have two different kinds of character in terms of their strength, in terms of their rock mass quality. Similarly, if you have joints in the rock mass, then depending upon different parameters related to the joint, for example, the overall number of joints per unit area or per unit volume, the length and depth persistence of joints, the aperture along the joint surface, the roughness along the joint surface, all these are going to play a very important role in characterizing the rock mass for many different structures. The structures which we have, civil engineering structures, they may be building, they may be road, they may be railway tracks, they may be dams, they may be tunnels or any underground structures. All these structures, when they are made, they have to confront these geological structures. So, let us start first with the importance of joints. The joints actually, they separate a rock mass into different kinds of blocks, and these block size and block shapes, they play a very important and major role when we go for loading the rocks by founding some structures, or when we go for unloading the rocks by large scale excavations. Now let us talk a little bit more about the joints, because this is a deformation structure which is the most common deformation structure, and this creates discontinuity in the rock mass. The presence of joints, depending upon how many number of joints are present per unit area or per unit volume, they will divide a rock mass into blocks of different sizes and shapes. For example, if the joints they are present at 2 meters apart, then if you have 3 sets of joints, then it will create a cube of 8 cubic meters. Similarly, if you have joints at 2 centimeter apart and if you have 3 sets of joints, then it will create a cube of 8 centimeter cube. So, the presence of joints will divide a whole rock mass into various discrete blocks. And when you load a rock or unload a rock mass will start moving along these discrete blocks and planes. So, joints are very important. So, whatever engineering classification of rock masses are there, they have incorporated different parameters of joints into them. For example, joint spacing, the distance between the two fracture system, number of joint sets, the aperture or the opening along the fracture, the filling material into that fracture, the roughness of the joint surface, the presence of groundwater along these joint planes. All these are going to play the major role in the behavior of rock mass whenever we go for construction on these grounds. Now, how to improve the condition? Closer are the joints, weaker will be the rock mass. More is the opening of the joints, poorer will be the rock mass. Planar is the joint surface or slick and sided is the joint surface, less will be the frictional resistance along the joint surface. So, all these things can be improved. How? By sealing these fractures through grouting or by connecting the blocks through rock bolting, or if you have very large size blocks, then you can connect through the rock anchors. So, in this way you can improve the rock mass strength by strengthening the rock along the joint surface. Now, these joints, they are very important features as far as landsliding is concerned. If you are going for constructing a road or rail network on a slope, then these joint planes, they are going to allow the rock blocks to slide over them. So, the infilling material plays a very important role. If you have infilling material that is sand and gravel, then you may have somewhat higher frictional resistance. But if the clay is filled in these joint plane, then as and when this clay absorbs water, then it starts acting as a lubricant and the block of rock may slide along these joint planes. So, joints are very important, they have to be looked very seriously and they have to mended before or during the excavation or construction. Similarly, shear zones after the joints, the most important deformation structure which we are going to encounter in the rock mass is shear zone. Shear zones, they are partly brittle and partly ductile deformation. Along the shear zones, the character of rocks totally change, and when it is changed, then what you have weak rock mass along the shear zones. The shear zones may come in different fashion, they may be of different types, they may be of different thickness, they may be of different lengths, but most importantly along the shear zones rocks may be pulverized. The rocks may be pulverized to very fine grained material termed as gouge. The rock may be pulverized to somewhat coarse grained material, that is sand sized material, that is called as mylonite, and the rocks can also be pulverized to a gravel sized material which we call breccia. Whenever you have shear zones, the rocks will be very weak along the shear zones, and the groundwater will also find place to reside along the shear zone. If a rock mass has very low amount of groundwater, along the shear zones it will have very high amount of water, as well as it will also have high permeability along the shear zones. So, shear zones are next to joints as far as deformation structures are concerned, and the way out to counter these shear zones are to hack them out and backfill by concrete, lean concrete or reinforced concrete. Sometimes we also go for grouting the shear zones if it is very deep seated. If it is close to the earth surface, then we will try to excavate it and fill it back with the concrete. Next very important structure is fault. Faults are not that common as compared to shear zones and joints, but if fault is there, if your structure is of large length, for example tunnels may have very large length dimensions, and then it may come across your tunnel. Similarly, if you have dam having a very large axis length, then again the fault may come into your structure. We will try to first find out that is this fault an active fault or dead fault. There are various methods to work out the antiquity of a fault. Those are the geophysical and geochemical methods. Once you are sure enough that the faults are active, then we should first try to realign our structure, because active faults can always result into movement. Along the fault also we find gouge, mylonite and breccia. Because of movement along the two fault planes, the rocks are crushed. There again we have to take this loose and weak material along the fault zone and we have to fill it with the concrete. But the most important thing is that we should avoid fault, and if we cannot avoid fault, then fault should come at 90 degree to your structures, so that you can have minimum of their effect on your structures. Now, faults also result into the repetition and omission of rocks. So, if you have structures constructed in a faulted area, then the same rocks may keep occurring. So, that is very important, that you have to see that your structure lies on same rock. If it is present on many different rocks, then again you will have problem of settlement and problem of rock strength as compared to the loading exerted by the structures. Now, the fourth very important structure is fold. The folds are the result of ductile deformation of rocks, and when the rocks undergo ductile deformation, they are thrown into anticlines and synclines. The dimensions of these anticlines and synclines may vary from few centimeters as far as their wavelength is concerned to hundreds of kilometers. Now, it all depends that what is the length of your civil engineering structure, how it is going to accommodate these anticlines and synclines. If the length of civil engineering structure is more, the wavelength of the fold is less, then you may have few anticlines and few synclines below your structure or along your structure. But if the wavelength of the folds are more than the length of your civil engineering structures, then you may have only part of anticline or part of syncline along or below your structure. Now, when we have folding, what we have, we may have repetition of rocks. So, again same rocks may be strong or weak, may keep coming after some distance below your structures or along your structures. In folding, when we have anticlinal zones, normally we have tensile stresses along the anticlinal zones. The presence of tensile stresses along the anticlinal zones will result into the formation of lot of fracture system. So, anticlinal zones are usually weak as compared to synclinal zones, where you have compressive stresses and number of fractures are less. So, if you are making any structure, then you have to come across with many fracture system in anticlinal zone and less fracture system in synclinal zone. For example, if you are making a tunnel, it will be difficult to make tunnel along the synclinal zone because of compressive stresses. The rocks will have very high strength. So, the rate of driving tunnel will be very less. But once you have same tunneling operation in anticlinal zone, then what you have weak rocks and your rate of tunneling may be increased. But in tunnels having anticlinal zone will have to have more of support system as compared to tunnels which are in the synclinal zone. But we may have problem related to the residual stresses in synclinal zone more as compared to anticlinal zone. So, faults depending upon its length will affect our structure. So, if we can see the next structure which is not exactly a deformation structure, that is a structure which is resulting due to the upheaval of the earth system, that is called as unconformity. We may have different kinds of unconformity with different kinds of time elapsed along those unconformable surfaces. Along unconformity also we have to be very cautious, because across the unconformity surface you will have two rocks of different kinds and different ages, and they may have different kinds of deformation structure across the unconformity surface. Also, it is very common to have residual conglomerates and paleosols along the unconformity surface, which are very weak material. In fact, some of the dams have failed because their foundation was laid on the unconformity surface, and the residual conglomerates, which seems to be very strong and robust, once water seeped into them, they failed and whole dam foundation got failed. So, the structures, they play very important role, and if you see the importance of these structures, then first and foremost will come the joints, followed by shear zones and contacts of the rocks, then primary structures, that is layering in the rocks, and then finally fault and fold. To summarize the deformation structures and their importance in civil engineering constructions, we have seen that we have contacts, primary structures and deformation structures. The primary structures, that is layering in different types of rocks, starting from lamination, foliation plane, bedding plane to flowage plane. Then we have contacts which are in between two different rocks, and then we have some important deformation structures. The most important ones are joints and shear zones, followed by faults and fold. The joints, because they are always present, they have to be looked with lot of seriousness, because they are going to control the overall rock mass behavior. The contacts, if are present, then what you have to see is that across the contact you may have two different rocks with two different mechanical properties and rock mass properties. In the case of shear zones, they may be present occasionally in the rock mass. If you can find them out, then it is better to hack them, to excavate them and to fill it by concrete. Shear zones, they are the avenues of groundwaters, and groundwaters, they are not good for any civil engineering structures. So is the case with the fault and fault zones. Along fault and fault zones also we get myelonites, we get gouge, we get breccia of different thickness and of different lengths. We have to excavate them and we have to backfill it with the concrete, because they are going to be very detrimental for any civil engineering structures, may it be road, may it be railway track, may it be foundation of dams, may it be tunnel across them. When we come to the faults, then depending upon the wavelength of faults and the length of the structures, we have to see that what part of faults we are working in. It is better to work in synclinal zone because there you will find much stronger rock as compared to anticlinal zone, where you will have added fracture systems because of tensile stresses in the anticlinal areas. But you have to see that in what way the groundwater system is moving through those rocks, and the groundwater seepage has to be checked. As far as unconformities are concerned, across the unconformity surface, we have altogether different rock mass, not only in terms of their type, but also in terms of their age, and the two different rock mass across the unconformity may also have different kinds of deformation structures, different kinds of mechanical behavior, and different kinds of rock mass condition. So, the deformation structures, they are to be looked in different ways, and accordingly we can either improve the rock mass by doing some external strengthening measures, or you may have to realign your structure, civil engineering structure, to avoid any active fault or any adverse folding conditions. Thank you.